May 11th, 1945. Radar picket station. 40 miles northwest of Okinawa. Lieutenant Commander Baron Mullaney stood on the bridge of the USS Hadley, watching the horizon turn black with aircraft. Not clouds, not a weather front. Japanese planes, more than 150 of them, inbound at wave-top height, and his destroyer had exactly 4 support craft and 1 other destroyer to meet them. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Hadley's 5-inch guns could throw shells 7 miles into the sky at a rate of 15 rounds per minute. On paper, that meant devastating firepower. In reality, hitting a maneuvering aircraft at 5 miles with a timed fuse was like trying to thread a needle while riding a roller coaster in the dark. The mathematics were brutal. Set the fuse timer too short, your shell explodes harmlessly below the target. Set it too long, the shell sails past and detonates in empty sky. And kamikaze pilots didn't fly predictable patterns. They jinked, they dove, they climbed, they did everything possible to make calculating a fuse setting impossible. But Mullaney's shells weren't using timed fuses anymore. They were using something the Japanese High Command didn't know existed, something German engineers had concluded was theoretically impossible, something that would turn the next 95 minutes into the most intense air-sea battle in naval history. The shells loaded in Hadley's magazines contained a complete miniature radio station in their nose, smaller than a wine bottle, packed with glass vacuum tubes that had somehow survived being fired at forces of 20,000 times Earth's gravity. The proximity fuse, and it was about to save his ship. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem that led to this moment had been obvious since the first aircraft dropped the first bomb on the first warship. Anti-aircraft fire was embarrassingly ineffective. In the early years of World War II, it took an average of 20,000 shells to down a single enemy aircraft. Some estimates ran as high as 100,000 rounds per kill. The mathematics were simple and cruel. Aircraft moved at 300 miles per hour. Shell flight time to altitude was measured in seconds. In those seconds, the aircraft traveled hundreds of yards. Gunners had to predict where the plane would be, set a mechanical timer on each fuse, fire, and hope. Hope the plane didn't change altitude. Hope the fuse timer was accurate. Hope the shell reached the right spot at the right instant. Most shells exploded in empty air. The few that came close enough to matter were statistical flukes, random chance masquerading as skill. Naval commanders watched helplessly as Japanese dive bombers pressed home attacks, as German Stukas screamed down on convoys, as their own ships burned from hits that superior anti-aircraft fire should have prevented but couldn't. The concept of a proximity fuse had existed for decades. Make a fuse that detects when it approaches a target and detonates automatically. Simple in theory, impossible in practice. Germany had explored proximity fuses as early as 1930, developing over 30 different designs. They tried acoustic sensors that would trigger on engine noise. They tried electrostatic detectors that would respond to charged aircraft surfaces. They tested optical systems and magnetic systems, and every variation their engineers could conceive. By 1939, German researchers had concluded the technical challenges were insurmountable. The components available in the 1930s were simply too large, too fragile, too unreliable. A proximity fuse needed to fit inside an artillery shell, survive the violence of being fired from a gun, and function perfectly during a few seconds of flight. The technology didn't exist. Adolf Hitler's leadership issued directives in 1940 prioritizing projects that could reach production within 6 months to support the coming invasion of the Soviet Union. Germany's proximity fuse programs were among the casualties. Though limited work would resume in 1944, far too late to affect the war's outcome, the British had reached further. By 1939, researchers at the Telecommunications Research Establishment had conceived of using a small Doppler radar system. They built prototypes. They tested them on rockets, which faced far less severe acceleration than gun-fired shells. But Britain's program was stopped by two critical obstacles. The cost was astronomical, and Britain's industrial capacity was already stretched to breaking. More fundamentally, they couldn't solve the miniaturization problem. The smallest vacuum tubes available, those used in hearing aids, were still far too delicate to survive the violent acceleration of being fired from a gun. A 5-inch naval shell, when fired, accelerates from 0 to 2,600 feet per second in roughly 20 feet of gun barrel. That creates an acceleration force of 20,000 times the force of Earth's gravity. Every component inside the shell experiences a crushing force equivalent to being hit by a sledgehammer. Glass vacuum tubes, with their delicate internal filaments and grids, shattered instantly under such stress. By 1941, British scientists had working prototypes that functioned perhaps 50% of the time under ideal conditions. For military use, this was inadequate. Ships needed weapons that worked every time, not half the time. The British shared their research through the Tizard mission when America entered the war, but it would be American scientists and American industry that actually made it work. In August 1940, as the Battle of Britain raged in the skies over England and the U-boat campaign strangled Atlantic shipping, the National Defense Research Committee faced a stark request from the U.S. Navy. Develop a proximity fuse that works, or watch American ships burn. The Navy's concern was visceral and immediate. Japan's naval aviation had proven devastatingly effective in the Pacific. A single aircraft, properly handled, could cripple or sink a capital ship worth tens of millions of dollars and crewed by thousands of men. The Pearl Harbor attack, still more than a year in the future, would validate every nightmare scenario Navy planners had imagined. The committee turned the problem over to Section T, a specialized research group at the Department of Terrestrial Magnetism, part of the Carnegie Institution of Washington. Leading Section T was Merle Tuve, a physicist whose brilliant but volatile temperament would drive a team that eventually numbered over 1,000 scientists and engineers. Tuve wasn't interested in theoretical elegance. He was interested in results. He had a sign posted on the laboratory wall that captured his philosophy perfectly. "I don't want any damn fool in this laboratory to save money. I only want him to save time. Shoot at an 80% job. We can't afford perfection." When Tuve's team examined the problem in September 1940, they faced a technological puzzle that seemed unsolvable with existing components. A proximity fuse needed to be small enough to fit in the nose of a shell, leaving room for 7 pounds of high explosive. Inside this tiny space, engineers had to pack a complete radio transmitter and receiver, a power source, safety mechanisms to prevent premature detonation, and a trigger circuit. All of this had to function in extreme temperatures, survive storage for months, and work perfectly after being subjected to forces that would pulverize normal electronics. The team settled on using radio waves and the Doppler effect. A miniature transmitter in the nose of the shell would emit continuous radio waves at approximately 180 to 220 megahertz. When these waves struck a target and reflected back, the frequency would shift due to the Doppler effect, the same principle that makes a passing train whistle change pitch. When the reflected signal reached a predetermined frequency, indicating the target was within lethal range, an electrical circuit would close and detonate the shell. The theory was elegant. Making it work required solving problems that the world's experts had already declared impossible. The first and most daunting challenge was developing vacuum tubes that could survive being fired from a gun. In 1942, a young physicist named James Van Allen joined the Applied Physics Laboratory, which had been established at Johns Hopkins University to house the growing proximity fuse program. Van Allen's task was to create what the team called rugged vacuum tubes, and the assignment seemed designed to fail. Van Allen started with miniature tubes that Raytheon and Sylvania had developed for hearing aids. These were the smallest vacuum tubes in existence, designed for the gentle environment of sitting in someone's pocket. Van Allen needed them to survive forces 20,000 times stronger. He began systematically redesigning every component. The glass envelopes were thickened and carefully annealed to reduce stress points. The internal filaments and grids were redesigned with shorter spans and heavier cross-sections to resist deformation. The mounting structure was reinforced, but redesigning on paper meant nothing without testing. Van Allen's team built a vertical gun at the Naval Proving Grounds in Dahlgren, Virginia. They fired shells containing prototype tubes straight down into soft earth. The earth caught the shells gently enough that researchers could recover the fuses and examine the tubes under microscopes to see exactly what had broken and how. Through hundreds of test firings and thousands of design iterations, patterns emerged. Certain glass compositions withstood shock better than others. Specific filament geometries survived, where others failed. Gradually, incrementally, the team developed tubes that could survive. In late 1940, they tried a desperate experiment. They mounted commercial vacuum tubes in metal blocks and dropped them off buildings, then examined the wreckage. Surprisingly, some tubes survived. It suggested the problem wasn't impossible, just extraordinarily difficult. They fired tubes from homemade cannons. They shot .22 caliber bullets at them. They subjected them to every form of violence they could devise, learning from each failure, incorporating each lesson into the next iteration. By September 1941, they were achieving success rates above 50%. The Navy, desperate for any improvement in anti-aircraft effectiveness, made a remarkable decision. They accepted that failure rate and authorized mass production tooling. The engineers were confident they could improve reliability during the production ramp-up. They were right. By early 1943, reliability had climbed above 90%. But vacuum tubes were only one challenge among many. The fuse needed a power source. Conventional batteries were too large and had limited shelf life, particularly in tropical heat where temperatures inside a shell could reach 140 degrees Fahrenheit. The National Carbon Corporation developed an ingenious solution, a reserve battery that used a liquid electrolyte kept separate from the battery plates until activation. When the shell was fired, centrifugal force from the shell's rotation spun the electrolyte into contact with the plates, generating electricity. This gave the batteries indefinite storage life. Until the shell was actually fired, the battery was inert and couldn't deteriorate. The fuse needed multiple safety mechanisms. It couldn't arm until well clear of the gun to protect the crew. It required protection against accidental detonation from radio interference or the ship's own radar. It needed sophisticated circuitry to prevent premature detonation when fired at low angles over water, where the shell might detect the ocean surface and explode before reaching its target. Each safety feature added complexity, but each was absolutely necessary. By the time development was complete, each proximity fuse contained approximately 130 miniaturized electronic components. The Mark 32 fuse for the Navy's 5-inch gun was 8 inches long and weighed just over 2 pounds. Inside its steel casing was perhaps the most sophisticated piece of miniaturized electronics that existed in 1942. The packaging difficulties were extraordinary. In an age before transistors or integrated circuits, fitting a working radar transceiver into a 5-inch shell seemed almost magical. On August 12, 1942, the light cruiser USS Cleveland conducted the first operational test in Chesapeake Bay. The target was 3 radio-controlled drone aircraft. Using conventional ammunition, downing these maneuvering drones typically required dozens of shots, and often the drones survived the entire exercise. Cleveland's gunners, firing proximity-fused shells, destroyed all 3 drones with just 4 bursts on the first day of testing. The Navy officers observing were stunned. The drone operators were devastated. They'd never seen their aircraft completely annihilated before and had no more drones to send against the Cleveland. They found a 3rd drone the next day. Cleveland's gunners brought it down almost immediately. The Navy immediately cancelled the remainder of the scheduled tests and ordered mass production to begin. 5 companies were selected to manufacture the fuses: Crosley Corporation, Radio Corporation of America, Eastman, Kodak, General Electric, and McQuay Norris. Production started slowly. By the end of 1942, factories were producing 500 fuses per day, but American industrial capacity was just warming up. By late 1943, production had reached 40,000 fuses per day. The Crosley Corporation in Cincinnati alone employed 10,000 workers operating continuously, 7 days a week, achieving peak output of 16,500 fuses daily. Sylvania Electric Products in Ipswich, Massachusetts produced 95% of all miniature vacuum tubes used across the program. Thousands of workers, many of them women, assembled the intricate components under conditions of absolute secrecy. Workers signed secrecy oaths. They were searched entering and leaving the facilities. They didn't know what they were building. They knew only that it was critical to the war effort and that their work might save American lives. Security surrounding the proximity fuse was second only to the Manhattan Project. The device was given the deliberately misleading code name VT Fuse, supposedly standing for variable time, to disguise its true nature as a radio proximity detector. The very existence of the fuse was classified top secret. Even its use in combat was initially restricted to situations where there was no chance of a dud falling into enemy hands. The Pentagon's logic was grimly simple. If Germany captured an intact proximity fuse and reverse-engineered the technology, the strategic air campaign over Europe might become impossible. Intelligence analysts estimated that German anti-aircraft guns equipped with proximity fuses could increase bomber losses by 300%. At those casualty rates, the bombing campaign would have to stop, so the fuses were used only over water, where dud shells would sink beyond enemy reach. When a dud proximity-fused shell landed on Sicily during the invasion in July 1943, headquarters dispatched a special patrol to recover it before German forces could find it. The patrol succeeded. The secret remained intact. The first combat use came on January 5, 1943, off Guadalcanal in the Solomon Islands. 4. Japanese Aichi-D. 3. A dive bombers, called VALs by Allied pilots, attacked a U.S. Navy task force. The VALs were slow and obsolete by 1943 standards, but they remained dangerous due to their accuracy and durability. One scored a hit on the New Zealand light cruiser Achilles before the group broke off their attack. As the Japanese aircraft departed, Lieutenant Commander Red Cochran, commanding the aft 5-inch battery on the cruiser USS Helena, fired 3 salvos of proximity-fused shells at the retreating bombers. All 3 shells exploded near one of the aircraft, shredding it with shrapnel. The aircraft plunged into the sea. Helena's gunners had achieved what would have required dozens of conventional shells. They had downed an enemy aircraft without scoring a direct hit, from a range where conventional time-fused shells would have been useless. Word of the success spread rapidly through the Pacific Fleet. By mid-1943, substantial quantities of proximity-fused ammunition were being shipped to Pearl Harbor. Combat results exceeded every prediction. In 1943, proximity-fused anti-aircraft fire was credited with more than half of all Japanese aircraft downed by naval gunfire, despite proximity fuses being used in only 25% of shells fired. That meant the fuse was outperforming traditional rounds by a ratio of 3-to-1 in routine combat conditions. Admiral Arleigh Burke, later Chief of Naval Operations, recalled that when he served as Chief of Staff to Admiral Mark Mitcher commanding the fast carrier task forces, proximity fuses knocked down enemy planes by the dozens. The psychological impact on American sailors was profound. For the first time in the war, they had a weapon that worked. For the first time, they weren't throwing up curtains of steel and praying that random chance would bring down an attacker. The shells were smart. The shells knew when to explode. But for Japanese pilots, the proximity fuse was a nightmare they couldn't understand. They would press an attack, see the American ship's guns fire, and then watch shells explode all around them without any visible impact point. It was as if the Americans had learned to make shells explode by magic, detonating at precisely the right moment to maximize shrapnel effect. Some pilots reported it to their superiors. The reports were dismissed as combat stress or exaggeration. The truth, that the Americans had developed miniature radar systems small enough to fit inside artillery shells, seemed too fantastical to be real. By mid-1944, the proximity fuse had fundamentally altered the calculus of naval warfare in the Pacific. Japanese losses to anti-aircraft fire were climbing. Conventional dive bombing and torpedo attacks were becoming unsustainable. The success of the proximity fuse, combined with radar-controlled fire direction and effective combat air patrols, had made normal attacks on U.S. task forces nearly impossible. The Japanese response was born of desperation and tactical logic. If pilots couldn't survive to return from attacks anyway, why not guarantee that each sortie inflicted maximum damage? The Kamikaze program began in October 1944 during the Battle of Leyte Gulf. The name meant Divine Wind, a reference to the typhoons that had destroyed Mongol invasion fleets in the 13th century. The tactic was brutally simple: load an aircraft with explosives and fly it directly into an enemy ship. The first organized kamikaze attack struck the escort carrier USS Streetlow on October 25, 1944. The carrier sank in less than 30 minutes. Over the following months, kamikaze attacks would sink dozens of ships and damage hundreds more. The tactic exploited a fundamental weakness in naval defense. Even the best anti-aircraft fire needed time to work. Proximity fuses were devastating, but they weren't instantaneous. A shell needed to reach the target area and detonate. Against a kamikaze diving at 300 miles per hour, every second mattered. Traditional naval tactics assumed pilots would break off attacks if damaged, seeking to survive and fight another day. Kamikaze pilots didn't break off. They pressed home attacks even after taking hits that would have sent conventional pilots fleeing. A kamikaze struck by proximity-fused shells and trailing fire would often maintain course long enough to crash into its target. The ballistic trajectory of a dying aircraft was enough. American commanders adapted their tactics. Ships were stationed on radar picket duty, positioned far from the main fleet to provide early warning of incoming attacks. These picket ships bore the brunt of kamikaze assaults, sacrificing themselves to protect carriers and battleships. It was brutal. Necessary mathematics. Better to lose a destroyer than a carrier. Better to fight the kamikazes as far from the invasion force as possible. The campaign for Okinawa, beginning April 1, 1945, represented the largest and most sustained kamikaze offensive of the war. The Japanese Fifth Air Fleet, commanded by Vice Admiral Matome Ugaki, had prepared 10 massive kamikaze operations codenamed Kikusui, or floating chrysanthemums. Each Kikusui might consist of more than 350 aircraft, including bombers, fighters, even obsolete biplanes. Some carried a terrifying weapon called the Oka, or cherry blossom, a rocket-powered flying bomb with over 2,600 pounds of explosives. The mathematics of Okinawa were staggering. From April through June 1945, the Japanese would launch over 4,500 kamikaze sorties against American forces. The casualties were grievous on both sides. The Navy lost 21 ships sunk and 66 damaged from kamikaze attacks. Thousands of American sailors died, but the proximity fuse was keeping the losses from being catastrophic. Without it, the invasion of Okinawa might have become unsustainable. On the afternoon of May 10, 1945, the destroyer USS Hadley received orders to take up station at Radar Picket Station 15, approximately 40 miles northwest of the Okinawa transport area. Joining the Hadley was the destroyer USS Evans and 4 smaller support craft. The Hadley was an Allen M. Sumner-class destroyer, commissioned just 5 months earlier in November 1944. She had arrived at Okinawa on April 27th and had already fought off numerous air raids. Commander Baron Mullaney, the Hadley's commanding officer, understood the assignment. Radar picket duty was the most dangerous job in the Navy. Picket stations were deliberately positioned to intercept kamikaze raids before they reached the main fleet. The ships stationed there were targets by design, but the Hadley had one advantage. She carried proximity-fused ammunition for her 5-inch guns, and she'd been designated as a fighter direction ship, meaning she could control the combat air patrol of friendly fighters, vectoring them toward incoming threats. That evening, the Hadley shot down 1 Japanese aircraft, a Kate torpedo bomber that approached just after 1930 hours. Throughout the early morning hours of May 11th, the crew remained at general quarters as enemy aircraft prowled the area on reconnaissance missions. At dawn, The radar screens began filling with contacts. Kikusui No. 6 was inbound. Over 150 Japanese aircraft were converging on the picket stations from multiple directions. These weren't just kamikazes. The raid included conventional bombers, fighters providing escort, and enough aircraft to overwhelm the defenses, through sheer numbers. The Hadley's radar operators watched the contacts multiply. The Combat Air Patrol, just a handful of American fighters, was vectoring toward the largest groups. But there were too many targets. At 7:40 in the morning, a Japanese E-13A Jake float plane approached the Hadley undetected by radar, flying low over the water. A Combat Air Patrol fighter was in pursuit. The Jake was hit and exploded in a massive fireball. It was impossible to tell whether the Hadley's guns, the Evans guns, or the pursuing fighter had made the kill. The wreckage splashed into the sea. Then the main attack began. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. At 8:35, an unidentified Japanese aircraft closed on the Hadley from the starboard beam. Both the Hadley and the Evans opened fire with their 5-inch guns. The proximity-fused shells bracketed the aircraft, and it splashed dead ahead of the Evans. 4 minutes later, a Mitsubishi A-6M Zeke fighter approached from high on the starboard quarter in a steep dive. The Evans 5-inch battery opened fire at 7,000 yards. The Zeke was shot down in flames at 2,500 yards, close enough that the crew could see the pilot still in the cockpit as the aircraft hit the water. At 8:41, another Zeke approached in a suicide dive from the starboard quarter. The 40mm and 20mm guns tore it apart. The aircraft hit the water 800 yards off the starboard beam, so close the Evans crew felt the spray from the impact. 2 minutes later, a Kawasaki Ki-61 Tony fighter approached on the port bow in a shallow dive at high speed. The main battery engaged at 5,000 yards. Hits were observed. The aircraft splashed close aboard the Hadley. Less than 2 minutes after that, another Tony approached from deep on the port quarter in an extremely steep dive. The 40mm and 20mm guns set it on fire, but the aircraft kept coming, smashing into the Evans port side near the waterline. The explosion killed several men instantly and flooded compartments. The Evans continued fighting. At 8:54, a Tony approaching from the port bow was engaged by both destroyers' main batteries at 7,000 yards. Hits were observed from both ships. The aircraft was shot down at 3,500 yards, an equal distance between the two destroyers. 2 minutes later, a Yokosuka D-4Y Judy dive bomber came in high and deep on the port quarter. The Hadley's guns opened fire at 6,000 yards. The Judy was set on fire and attempted a suicide run, but appeared out of control. It crossed over the ship and crashed in the water 2,000 yards off the starboard bow. The action was becoming continuous now. No breaks between attacks. The Japanese were pressing home their assault in waves, multiple aircraft coming from different directions simultaneously. The Hadley's gun crews were loading and firing as fast as physically possible. The barrels of the 5-inch guns were heating up. Proximity-fused shells were being brought up from the magazines in an endless chain. At 8:58, a Yokosuka P-1Y Francis bomber approached from the starboard quarter. The 5-inch battery engaged. The Francis exploded in mid-air at 4,000 yards, torn apart by proximity-fused shells that detonated within 75 feet of the aircraft. At 9:02, another Judy approached. Shot down. At 9:05, a Nakajima B-6N Jill torpedo bomber. Shot down. The Combat Air Patrol was fighting desperately overhead, tangling with Japanese fighters and bombers, but there were simply too many targets. The Hadley's fighter direction officers were vectoring friendly aircraft as fast as they could speak, but the Japanese kept coming. By 9:10, the Hadley had shot down or assisted in destroying over a dozen aircraft. But the gun crews were tiring, ammunition handlers were exhausted, and the attack showed no signs of stopping. At 9:13, a Judy dive bomber came screaming down from high altitude directly toward the Hadley. The 5-inch guns tracked it, firing proximity-fused shells in a steady stream. The Judy took multiple hits but kept coming, trailing fire and smoke. It crashed into the Hadley's forecastle, destroying the forward 5-inch gun mount. The explosion killed several men and started fires. 30 seconds later, another aircraft, a Tony, struck the Hadley amidships on the port side. The explosion was catastrophic. Fuel from the aircraft sprayed across the deck and ignited, creating a wall of flame. The blast destroyed the ship's portside 40mm guns and killed or wounded most of their crews. Worse, the explosion ruptured fuel lines and started fires throughout the midships section. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. At 9:15, as the crew fought fires and casualties mounted, a Yokosuka MXY-7 Oka flying bomb struck the Hadley aft. The Oka was a rocket-powered guided bomb, essentially a manned missile with over a ton of explosives in its nose. The impact and detonation were devastating. The explosion tore a massive hole in the Hadley's stern, flooded the engineering spaces, and knocked out power to the aft section of the ship. Then, at 9:17, a fourth aircraft crashed into the Hadley's superstructure. The destroyer was now dead in the water, listing to starboard, with fires burning amidships that were detonating ammunition. The fantail was awash. The engineering spaces were flooded. Most of the ship's weapons were out of action. Over 30 men were already dead. Another 67 were wounded, many seriously. Commander Mullaney assessed the situation with brutal clarity. His ship was dying. The fires were spreading toward the magazines. If the main magazines detonated, the Hadley would simply disintegrate. But Japanese aircraft were still attacking. The Evans was also heavily damaged, having taken 4 kamikaze hits and fighting for survival. Mullaney gave an order that would echo through naval history. Hoist all available colours. If this ship is going down, she's going with all flags flying. The Hadley's remaining gun crews, many of them wounded, kept firing. The ship had no power, no ability to manoeuvre, and was settling deeper into the water. But the few operational guns continued engaging targets. One 5-inch mount was still firing, its crew manually loading and aiming without power assistance. The proximity fuses were still working. Even dead in the water, even burning and flooding, the Hadley was still killing attacking aircraft. At that moment, salvation arrived in the form of 4 additional U.S. Navy fighters that had been vectored to the picket station. The fighters tore into the remaining Japanese aircraft with a fury born of desperation. They knew the destroyers below were dying and that every second mattered. The pilots pushed their aircraft to the limits, making gun runs at dangerous angles, pressing attacks to point-blank range. The combination of the fighters and the Hadley's remaining anti-aircraft fire broke the back of the Japanese attack. Aircraft began turning away. Some had exhausted their ammunition. Others, low on fuel, headed back toward their bases in Kyushu. The horizon, which had been filled with attacking aircraft 15 minutes earlier, was suddenly empty except for smoke and wreckage. Commander Mullaney ordered most of the crew over the side into life rafts. Approximately 50 officers and men remained aboard to fight fires and attempt to save the ship. The situation was desperate. The Hadley was listing heavily to starboard. The fantail was completely underwater. Fires were still burning amidships, setting off ammunition periodically. The torpedoes in their tubes represented another danger. If the fire reached the Torpex explosive in the torpedo warheads, the resulting explosion would vaporize what remained of the ship. But the damage control parties were winning. Slowly, agonizingly, they brought the fires under control. They shored up bulkheads. They pumped water from flooded compartments. The Hadley remained afloat, though barely. The destroyer was towed to Ie Shima for emergency repairs, then to Karama Reto, then to Buckner Bay on Okinawa. Eventually, in July, the Hadley began the long journey home under tow, 6,100 miles to San Francisco. The final accounting from the morning of May 11th, 1945, was extraordinary. The USS Hugh W. Hadley had shot down 23 enemy aircraft during approximately 95 minutes of continuous combat. The USS Evans had shot down 15 more and assisted in the destruction of 4 others. Together, the 2 destroyers and their 4 support craft had faced over 150 attacking aircraft and destroyed at least 38 of them. 23 aircraft shot down by a single destroyer in one engagement remains an all-time naval record. The Hadley received the Presidential Unit Citation. 121 Purple Hearts were awarded to her crew. 20 individual medals for valor were presented, but the ship herself was too damaged to repair. She was decommissioned on December 15, 1945, and sold for scrap in September 1947. The Evans survived her damage and was repaired, serving in the Navy until 1946. Her commanding officer, Commander Robert Archer, received the Navy Cross for his actions on May 11th. The citation noted that despite the ship being in sinking condition after taking 4 kamikaze hits, Archer had led his crew in determined efforts to save the ship and bring her safely to port. 28 men from the Hadley died that morning. Another 67 were wounded. The Evans lost several crew members as well. But without the proximity fuse, both ships would certainly have been sunk with far greater loss of life. The mathematics were inescapable. Against kamikazes at close range closing at high speed, conventional time-fused ammunition required anywhere from 960 to 1160 rounds per aircraft destroyed. Proximity-fused ammunition required just 310 rounds per kill. That difference represented the margin between survival and annihilation. The Hadley and Evans had fired thousands of rounds that morning, but proximity fuses had made every shell exponentially more effective. Shells that would have exploded harmlessly in empty sky with time fuses instead detonated precisely when they came within lethal range of their targets. The Japanese pilots had no defense against it. They couldn't see the shells coming. They couldn't evade the proximity-triggered explosions. They simply died, torn apart by shrapnel from shells that seemed to know exactly when to detonate. After the war, Japanese commanders were interviewed about American anti-aircraft effectiveness. They consistently described the uncanny accuracy of U.S. naval gunfire, the way shells seemed to explode at precisely the right moment, even when no direct hit had occurred. Some suspected the Americans were using some form of proximity detection, but they had no idea how it worked or how to counter it. The technology seemed almost supernatural. The Japanese had actually developed their own proximity fuse late in the war. It was fielded too late to be decisive and was deployed exactly once, in a dropped bomb. Japanese engineers simply couldn't match the American industrial capacity required to mass-produce such complex devices. Even if they'd solved the technical problems earlier, they lacked the factories, the workers, the supply chains, and the raw materials to produce proximity fuses in meaningful quantities. Germany never succeeded in fielding a working proximity fuse at all. When German forces captured unexploded American shells containing proximity fuses, their engineers examined them with something approaching disbelief. The miniaturization was beyond German capabilities. The rugged vacuum tube seemed impossible. German engineers had concluded years earlier that such devices couldn't be made to work reliably. The Americans had not only made them work, they were producing them by the tens of millions. A post-war analysis by German technical intelligence officers captured the psychological impact. One German engineer wrote that the proximity fuse demonstrated a fundamental difference in industrial capacity. American engineering, he noted, solved impossible problems through massive application of resources. The proximity fuse required extraordinary manufacturing capacity and acceptance of high costs. Germany could never have produced such a weapon, not because German engineers were less skilled, but because German industry couldn't support the required infrastructure. The production statistics told the story. Over the course of World War II, American industry produced more than 22 million proximity fuses at a cost exceeding $1 billion 1940s dollars, equivalent to approximately $15 billion today. More than 100 factories participated in some phase of production. At peak output, American factories were producing 70,000 fuses per day. Consider what that represented. 70,000 complete miniature radar transceivers manufactured every single day. each one containing 130 precision electronic components, each one assembled by hand under microscopes, each one tested to ensure it would function after being subjected to forces that would destroy normal electronics. The scale was staggering, the quality control unprecedented, the logistics mind-boggling. Crosley Corporation alone produced over 5 million fuses, employing 10,000 workers around the clock, 7 days a week. Sylvania manufactured nearly 6 million fuses, while also producing 95% of all miniature vacuum tubes used across the entire program. The coordination required to bring together 87 different companies using 110 factories, all working on a top-secret project where most workers didn't even know what they were building, represented an organizational achievement nearly as impressive as the technical innovation itself. The secrecy remained absolute until September 1945, after Japan's surrender. When the proximity fuse was finally revealed to the public, the reaction was astonishment. The newspapers called it one of the war's best-kept secrets, second only to the atomic bomb. Winston Churchill stated that the proximity fuse had proved potent against the German V-1 flying bombs that had terrorized London in 1944. General George Patton called it the funny fuse and credited it with winning the Battle of the Bulge. Secretary of the Navy James Forrestal wrote, "The proximity fuse has helped blaze the trail to Japan. Without the protection this ingenious device has given the surface ships of the fleet, our westward push could not have been so swift, and the cost in men and ships would have been immeasurably greater." Vannevar Bush, who had overseen the entire development effort, credited the proximity fuse with 3 significant effects. It was important in defense from Japanese kamikaze attacks in the Pacific, where Bush estimated it increased the effectiveness of 5-inch anti-aircraft artillery by 7 times. It was essential in neutralizing German V-1 attacks on England, and it changed the tactics of land warfare in Europe, where proximity-fused artillery shells proved devastatingly effective against personnel. The strategic impact extended far beyond the immediate battlefield effects. The proximity fuse forced both Germany and Japan to fundamentally alter their tactical doctrines. German units in Europe began dispersing more widely to reduce casualties from proximity-fused artillery airbursts. Japanese commanders shifted from conventional attacks to kamikaze tactics, partly because conventional attacks had become too costly against proximity-fused anti-aircraft fire. Admiral Lewis Strauss wrote after the war, "One of the most original and effective military developments in World War II was the proximity, or VT, fuse. While no one invention won the war, the proximity fuse must be listed among the very small group of developments, such as radar, upon which victory very largely depended." General Dwight Eisenhower acknowledged the contribution in stark terms. He suggested that if Germany had succeeded in perfecting and using proximity fuses 6 months earlier than the Allies, the invasion of Europe would have proven exceedingly difficult, perhaps impossible. The counterfactual was chilling. German anti-aircraft defenses equipped with proximity fuses might have made the D-Day landings unsustainable. German artillery using proximity fuses during the Normandy campaign could have inflicted casualties that halted the Allied advance entirely. The technological legacy of the proximity fuse extended far beyond military applications. The miniaturization techniques influenced the entire electronics industry in the decades after the war. The quality control methods developed for fuse production became standard practice in manufacturing worldwide. The workforce training programs demonstrated that complex technical work could be performed by people without advanced education, given proper training and supervision. James Van Allen, the physicist who had developed the rugged vacuum tubes for proximity fuses, later applied the same miniaturization techniques to scientific instruments for space exploration. The Explorer 1 satellite, launched on January 31, 1958, carried instruments that drew directly on proximity fuse technology. The knowledge gained from making electronics survive artillery acceleration helped make electronics that could survive rocket launches into space. Data from Explorer 1 led to the discovery of radiation belts circling Earth, which were named the Van Allen belts in his honor. The technology transfer went beyond space exploration. Engineers who had worked on proximity fuses went on to careers in the electronics industry, bringing expertise in miniaturization, quality control, and mass production. The proximity fuse's military impact extended through the Korean War, where American forces used improved versions with even greater reliability. Modern weapon systems use descendants of the World War II proximity fuse. The Phoenix missile, the Standard Missile family, and the Patriot surface-to-air missile all use proximity fuses based on the same fundamental concept developed in 1942. Today's fuses use solid-state electronics, microprocessors, and sophisticated signal processing. They can discriminate between real targets and decoys. They can operate in jamming environments, but the core principle remains unchanged. Detect the target using radio reflections, calculate the optimal detonation point, and trigger the warhead for maximum effect. The story of the proximity fuse is ultimately a story about what was considered impossible and what turned out to be merely difficult. In 1939, every major military power had examined proximity fuses and concluded they couldn't be built with available technology. The Germans tried for nearly a decade and gave up. The British made progress but couldn't solve the mass production problem. The Japanese developed a working prototype but fielded it too late to matter. Only the Americans succeeded, and they succeeded not because American scientists were necessarily more brilliant, but because American industry could support the required effort. The proximity fuse needed an economy that could allocate $1 billion to a single weapon system. It needed an industrial base that could mobilize over 100 factories for a top-secret project. It needed a workforce that could be trained to assemble intricate electronics while knowing nothing about what they were building or why it mattered. The development process took remarkable risks. The Navy accepted proximity fuses with a 50% failure rate and authorized mass production, gambling that the engineers could improve reliability before combat deployment became critical. That gamble paid off, but it required a level of institutional courage that was anything but guaranteed. Imagine the pressure on Merle Tuve and his team. They were promising to deliver a technology that experts worldwide had declared impossible. They were asking for resources that could have built dozens of ships or hundreds of aircraft, and they were racing against a clock measured in American lives. Tuve's philosophy of shoot at an 80% job rather than pursuing perfection was revolutionary in an engineering culture that prized precision and completeness. But Tuve understood something fundamental about wartime development. An imperfect weapon deployed in 6 months was infinitely more valuable than a perfect weapon that arrived after the war ended. Better to field fuses that worked 90% of the time immediately than to wait 2 more years developing fuses that worked 95% of the time. That pragmatic approach, combined with American industrial capacity, produced a weapon that changed warfare. Consider the human cost that was prevented. At Okinawa, proximity fuses helped shoot down hundreds of kamikaze aircraft before they could reach their targets. Each aircraft that was destroyed represented a ship that wasn't hit, crew members who weren't killed or wounded, and a campaign that didn't have to be abandoned due to unsustainable casualties. The Navy suffered grievous losses at Okinawa despite the proximity fuse. 21 ships sunk, 66 damaged, thousands of casualties. But intelligence analysts estimated that without proximity fuses, losses would have been 3 to 4 times higher. Instead of 21 ships sunk, it might have been 60 or 70. Instead of thousands of casualties, it might have been tens of thousands. The invasion of Okinawa might have become operationally impossible, forcing a reassessment of the entire strategy for defeating Japan. The USS Hugh W. Hadley's fight on May 11, 1945, encapsulated everything the proximity fuse made possible. A single destroyer, already hit 4 times and dead in the water, continued destroying attacking aircraft because her remaining guns were firing shells that knew when to explode. Those shells, each containing a miniature radio station that had been considered impossible to build just 5 years earlier, were the difference between the ship sinking with all hands and the ship surviving with heavy casualties. Commander Baron Mullaney's order to hoist all available colours as his ship appeared to be sinking wasn't just dramatic theatre. It was a statement about what the proximity fuse represented: American engineering had solved a problem the rest of the world thought was unsolvable. American industry had mass-produced a miracle, and American sailors, armed with that miracle, were going to fight until they won or died trying. The Hadley's crew didn't know the details of how proximity fuses worked. They didn't know about James Van Allen's rugged vacuum tubes or the reserve batteries or the Doppler effect circuitry. They just knew that when their shells exploded near enemy aircraft, those aircraft died. That was enough. That was everything. 23 aircraft shot down in 95 minutes. It remains a record because it represents the maximum effectiveness of World War II anti-aircraft technology pushed to its absolute limits. The Hadley's gun crews were firing as fast as physically possible. The proximity fuses were working as designed. The combination was devastating. But it wasn't magic. It was engineering, refined through thousands of test firings, implemented by workers who assembled components under microscopes, and deployed by sailors who trusted that the shells would work when everything depended on it. The post-war world inherited the lessons of the proximity fuse along with the technology itself. The lesson that impossible was often just another word for difficult. The lesson that technical challenges could be overcome through the application of sufficient resources and determination. The lesson that mass production of sophisticated electronics was achievable if you were willing to invest in the training, the facilities, and the quality control systems. These lessons would shape the Cold War arms race, the space race, and the development of modern consumer electronics. When President Kennedy announced the goal of landing on the moon, the engineers who worked on that program included veterans of the Proximity Fuse project. They knew that seemingly impossible technical challenges could be solved. They'd done it before with vacuum tubes that survived 20,000 G-forces. They could do it again with rockets that reached escape velocity. The proximity fuse also provided a template for large-scale secret weapons development programs. The Manhattan Project is more famous, but the proximity fuse project was in many ways more complex from a manufacturing and logistics standpoint. The Manhattan Project needed to produce a few atomic bombs. The proximity fuse project needed to produce millions of precision electronic devices. The organizational structures, security procedures, and production management techniques developed for the proximity fuse influenced every major weapons development program that followed. But perhaps the most important legacy was psychological. The proximity fuse proved that American industry, when mobilized for a common purpose, could achieve things that seemed beyond the realm of possibility. In 1940, when Merle Tuve proposed developing proximity fuses, the British had already concluded it couldn't be done at scale. The Germans had given up. Tuve and his team didn't give up. They tested vacuum tubes by dropping them off buildings and shooting them with guns. They fired experimental shells into the ground hundreds of times to examine what broke and why. They redesigned circuits and power supplies and safety mechanisms until everything worked. 5 years later, American factories were producing 70,000 proximity fuses per day, and those fuses were saving American lives in both the Pacific and European theaters. The Germans, examining captured American shells, couldn't comprehend how such miniaturization had been achieved. The Japanese, facing proximity-fused anti-aircraft fire, couldn't understand why their pilots were dying in such disproportionate numbers. The answer was simple and profound. One nation had decided that the impossible was merely difficult, had committed the resources necessary to prove it, and had succeeded. The proximity fuse wasn't the only weapon that won World War II, but it was among the handful of innovations that made victory possible, that kept casualties lower than they would have been, that shortened the war, and saved lives on both sides. On that morning in May 1945, as Commander Mullaney stood on the bridge of his burning, flooding destroyer and ordered all flags raised, he was fighting with a weapon that represented the best of American ingenuity, industry, and determination. The Hadley's guns fired shells that shouldn't have been possible to build. Those shells destroyed aircraft at ranges that conventional ammunition couldn't reach, and because of that, the Hadley survived. The ship was scrapped 2 years later. The crew dispersed civilian life. The proximity fuse was declassified and its story told. But the lesson endured. Technical problems that appear impossible today might simply require the right combination of talent, resources, and stubborn refusal to accept that it can't be done. Fuze didn't want his engineers to save money. He wanted them to save time. He didn't demand perfection. He demanded results. His philosophy produced a weapon that changed warfare and saved countless lives. The proximity fuse stands as proof that the greatest achievements often come not from brilliant individuals working alone, but from teams of dedicated people given a clear objective, adequate resources, and the freedom to fail repeatedly until they succeed. The miniature radio station packed into an 8-inch shell casing seemed impossible in 1940. By 1942, it was in mass production. By 1943, it was destroying Japanese aircraft over the Pacific. By 1945, it was keeping ships like the Hadley in the fight when they should have been sinking. And 70 years later, descendants of that same technology guide missiles and defend against threats in ways that would have seemed like science fiction to the engineers who started with vacuum tubes dropped off buildings. The proximity fuse worked because someone refused to accept that it couldn't be done, because an entire nation mobilized its industrial capacity to build the impossible, and because sailors like those aboard the Hadley trusted their weapons to work when everything depended on it. That trust was earned through thousands of hours of testing, millions of components assembled with precision, and a commitment to solving problems rather than accepting limitations. One engineer's impossible fuse became the weapon that made Navy shells explode near Kamikazes, and in doing so, it helped win a war and showed the world what was possible when impossibility was treated as just another engineering challenge, waiting to be solved. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.